Hello, 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 animated Vicky. Hello, um, hello, Mafine. Hello, Fabia. Hello, Cayenne. Hello. All right, I'm doing the chat now. Hello, Caitlin. Oh, that's interesting. Wait, sorry.
Good afternoon, Professor.
Oh, good afternoon, Abid. He used his voice. I mean, what? I'm so honored. That is points right there. That's awesome. Hold on, more people coming. Good afternoon. Thank you for saying so. And I'm not kidding. I don't mean to single. All right. So that's awesome. So, and good morning or afternoon, Joel. And good afternoon, Sonam. And I'm looking at as you can see, I'm saying hello first to people that have anything other than black boxes. I'm looking at the chat now. Wait. Um, yeah, yeah, yeah. So good morning, Fabia. Thank you for saying so. Good afternoon, Vicky. Oh, well, time flies while you're having fun. Okay. Vicky. Hello, Anthony. Good morning, Melanie. Good afternoon, Mafine. Good afternoon, Caitlin. Oh, how am I? Well, I'm lovely, thank you. I just got better just from the greetings in this class. Thank you. Good afternoon, Raina. Good afternoon, Joel. Good afternoon, Sonam. Good afternoon, Cayenne. Good afternoon, Gabriel. Good afternoon, Victoria. Good afternoon, Zoe. Oh, happy Wednesday. I like it. Yes, yes, happy Wednesday. Excuse me. Yeah, that's happy. Healthy Wednesday. Good afternoon, Bridget. Okay. Oh, good afternoon, Roger. Sorry, just skip Roger. Still more people coming. Okay. Um, and good afternoon. Who did I not? If I didn't say your, oh, still more people coming. Okay. Oh, and there's Lear. Good afternoon, Lear.
Hi, Professor. Good afternoon. How are you?
Good, thank you. Oh, we got a voice and a how are you? Good, thank you. Very good. Even better now. Thank you.
Good afternoon, Professor.
Oh, good afternoon, Mohammed. Look at this. This class is like on fire, or is fire. The class, that's what we say now, right? The class is fire. That's yes. Okay. For real. All right. So good afternoon, everybody. Okay. Okay. Wait. We're gonna start again. Oh, and there's Anthony. Oh, awesome. And David, so much video. I just can't even get over it. It's like it's like awesome. Um, okay. So we're going back. We're going to continue going over homework one now. What happened? Yeah. Um, sorry, we're going to continue going over homework one, maybe a little bit faster than we were before. The emphasis of last class was for me, I dragged out question one to show you what I'm looking for in the five-step method. Now, hopefully that's clear or getting clearer. That's what I'm looking for you. But so now I'm going to start going a little bit faster. Like from here on, I'm going to be talking about the physics. So I won't always be always clear about the five steps when I'm teaching something. I mean, I'll try to be sometimes, but my emphasis today will be on the physics. Hold on, I'm just mute. Okay. Um, so and again, warning, even with that, like I'm going to do some physics and review some physics that maybe some of you have seen before, but maybe you haven't, that we definitely need for the class. Um, So we will progress more through homework one today. But again, warning, we're not going to finish all of homework one today. Even though some more stuff is due, like next week. In fact, oh, let me be very clear about that. So we're still going to be dealing with homework one, even next week. That is how it always goes. Um, Two things. Of course, anything that I say in the class today or last time that helps you fix things or improve things in your homework one, of course, absolutely, you should use this new knowledge to go back and revise and re-upload and get more points on homework one, like until we're totally done with it. Absolutely, please do that. Um, but at the same time, you'll notice that there is a homework two, or excuse me, there's a homework 1B due next week. Just to warn you, that one is not mathematical or intricate the way this one is, and it's not yet mathematical and intense the way homework 2 is. In other words, I just want to quickly say homework 1B is intentionally assigned while we're still all talking about homework 1A. So you don't need to have finished homework 1A in order to do homework 1B. It's much more like just like a thought game, like an exploratory thing. It's not meant to be stressful. Don't take it overly seriously. It's meant to prompt a discussion. I'm talking about homework 1B now, the next thing that's due. Do it. Yes, please do it. Do it like responsibly, but don't get overly worked up about it. And yeah, for homework 1B, I should say clearly is an exception. You don't have to do the 5-step method of solving problems for homework 1B. It's not a problem solving thing. It's like a thought experiment thing. Okay. I hope that's clear. So homework 1B. So mainly what you're really doing in the background between now and the next time we meet is you're really trying to improve, revise, and fix homework 1A, like that I'm trying to give space and time to do that. Okay. Homework 1B is not meant to be a stressful um undertaking. Okay, hopefully that's
Professor, can I ask a question, please?
yes, absolutely.
Where am I supposed to see my grade for homework 1A?
You depending on when you turned it in, you might not have gotten it back yet. Let me look. All the ones that were if you didn't get it back yet, I apologize. If it came in early enough before Monday, then I sent it back. But if it came in right, even if it was
I
on
think
time,
it was Sunday.
oh, then wait, then I think, okay, well, let me look quickly. Or maybe you might hang out after class for a minute. Okay, if I can see this quickly, I will. But if there's an issue, I'll ask you just right after class to hold on.
Okay.
Okay, hold on. It's, oh, sorry. I just had it. Sorry. Oh, yeah. Okay, I apologize. Wait, why is it? For whatever reason, no, it's on my side. I don't know why, but I didn't get to yours yet. You don't have a grade yet. But that's not personal. You're not the only one. I, I don't know why that is though, but and
Okay,
if
but
you
can you see I submitted it on
oh,
time?
oh, 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 yes. No, not only can I see that you submitted it, absolutely, but I can also see that you submitted it on time. So
Okay, great.
that's, yeah, so it's on my side. Yeah, I apologize. But yeah, fair
No,
question.
that's okay. Okay,
Okay.
thank you. So
So you just wait for me to, like, I will do it soon. But yeah, you
okay,
just
and 1B is due on February 10th, right?
correct.
Okay,
But
great.
right. No, yeah. So good question. And definitely submit for the points for using your voice and everything. And to everybody, no, I'm glad he just asked because he's not alone. Like there are other people. I don't even know how that is because I could have sworn that I did all. But all right, yeah, there are other people who still haven't gotten back a homework one yet. That is on me. It but again, you don't. So there's nothing you can do until you get it back. But you don't need to understand homework 1A or something in order to do 1B. It's like off to the left. Everybody, just to be clear. But okay. So we're right. Okay, yeah. Why were there so many that? If he came in on Sunday, okay, yeah, no, he's not alone. Oh, and Melanie, right? Same thing with you. Okay, give me 1 second, because actually, I really thought in this class that I had done a ton of.
Well, I've submitted it. I submitted my homework the right before class, so that could
Oh,
probably be why.
okay, yeah. If you, yeah, and it's so this is not a punishment or anything, but right, if you submitted it right before class, then I just didn't because I don't because I travel on Tuesdays and and all Tuesday night. So if I don't do something Sunday or Monday, then I don't get to it till like Wednesday or Thursday. So yeah, that's on me, not on you. You're all right. Look, I'm going to say this right now. This is not to embarrass anybody. This is like a positive thing, not a negative thing. Just to be clear for anybody's concerns, if I say your name in a minute, it means not only did I totally get your homework, but I know for a fact it's on time. I just haven't done anything with it yet. Okay. If I say your name, if I don't say your name, that doesn't mean anything bad. It just means you can hang out after class and ask me whatever. But if I say your name, it means I totally have your homework 1A and I know it was on time and I just haven't gotten to it yet. So here they are. Thank you, Zoe. Thank you, Caitlin. Thank you, Latchman. Thank you, Melanie. Thank you, Lear. Thank you, Abid. Thank you, Mohammed. Thank you, Yadiah. Okay. If I didn't say your name, that does not mean there's a problem, but I'm just saying if I did say your name, you're definitely like the ball's in my court. Okay. If you have any question, you can hang out right after. I hope that's clarifying somewhat. Okay. Okay. Oh, and more people coming. Okay. So if that's okay, I'm going to now. Oh, and just so you know, too, for those of you who are getting used to me or how this works, whenever I have this board sitting up here, like the first page of the board of the PDF, like here, this is always these equations that are on the board are generally like the statement of what I'm trying to get to in the class. They don't mean if I have equations on the board, right, when you walk in, like this board right here, that doesn't mean that I'm assuming that you already know these equations, or it doesn't mean that I'm assuming that you were already supposed to use them. It means it's kind of like the agenda for the class. Okay, just so you know. So there, okay, just so you know. Okay. And sometimes I don't even get to them. They might then be the agenda for next class, but it's like a plan, not a. Okay, so I'm going to start going back over the homework 1A. Right, and this was a situation, as we know. Okay, so I believe, now stop me if I'm wrong, but I believe we did question one. Well, all right, just to sum, we did question one, we dragged it out, but we finally got an answer for question one. And the answer was that at x equals x naught, F equals negative 30 newtons, right? That was the answer to question one. Stop me if that's not true, but I think it is. So now I'm going to go to question two. And again, I'm not doing the method now. I'm just doing some answers and thoughts. So, okay. So question two was at x equals x naught, what is the value of a, right? What is the acceleration, right? And I'll cut, well, I believe that's the answer. Now, again, I'm going to say this one more time so there's no confusion. You can use anything I say now, you can use to correct your homework, but you, in your homework, still have to put out all the 5 steps. That's partly how you show that you understand. Okay. I'm not doing that now because I want to move on and like teach some physics. But so this is just that's just a quick, this is just my quick little work. But I believe that's the answer for question two. I took the answer from question one, I divided by the mass. So I got that the acceleration at the initial position is negative 100 meters per second squared. Uh, any questions about that? Like I'm gonna just keep moving. Please ask questions if you want. I'm gonna move as long as you don't, but I'm not moving to discourage you from. So, but if there's no questions, I'm gonna keep going. All right. So then question three. And if you're ever worried about it, just put a question in the direct chat. Like if you, right? And then I can decide if I really think it's not worth pausing for your question. Like I can decide that. But anyway, question three is then at x equals 0, what is the acceleration? And I believe that so question three is asking what's the acceleration? What's the instantaneous acceleration at when the mass is at the equilibrium position? Now I believe the answer is 0. Now again, how did I get that? Well, I did the same thing as in question two. I found the force. How did I find the force? F equals negative kx. You know, the work that I did for question one. F equals negative kx. plugged in 0 for x, so I got 0 for f. Then I do f net equals ma, I divide by m. So I get that the acceleration for the equilibrium position is 0. Now, I don't think you could still ask a question. I'm assuming the math is straightforward enough that the answer is not totally shocking to anybody, but I want you to notice a couple of things about this. Notice, first of all, we just asked the same question twice, but about two different positions. We just asked twice, what's the value of acceleration? But we asked it, what is it over here? And then what is it over there? And we got two answers. So even if they weren't like terribly hard to figure out, there's a reason we're being asked. The beginning of a physics problem often is asking you things that are not that hard to figure out. Don't overthink them. Don't think it's trying to trick you, but realize that it's probably trying to establish information that may be useful later on in the problem. So right now, what we've just established is that, because the force is changing continuously as a function of position, because the force is varying, therefore the acceleration is varying. The acceleration is not remaining constant from over here to over there. That's important observation. That's going to affect the rest of the situation, of the problem solving, that the acceleration is not a constant. Furthermore, notice okay, I want you to notice I want you to notice that at the equilibrium position, what we've just concluded is the acceleration is 0. That is not a coincidence. It's not a special circumstance. That, in fact, is what it means to be an equilibrium position. Equilibrium is where the forces are, in general in physics and in science, really. An equilibrium position is where all the forces are in balance, equilibrium. Therefore, the net force acting on an object in equilibrium, the net force is 0. Therefore, acceleration is 0. That's literally what it, like, in other words, whenever you're at an equilibrium position of any kind, your acceleration will be 0, as opposed to what people tend to unconsciously think about equilibrium positions. We often might think an equilibrium position is a place of rest, a place where there's no motion. That is not true necessarily. I mean, it's not true that, as we're about to find out in question 4, there can absolutely be motion at an equilibrium position. There can be speed, velocity. There just can't be change in speed or velocity. So an equilibrium position is a place where if you put something there, if you start something with no velocity at equilibrium, then it won't change its velocity. It will stay at that velocity of 0 forever. So an equilibrium position is the one and only place where if we put something there, then it will stay there. But it doesn't have to mean that things can't move through there. Okay, that's just an observation. That's what equilibrium means. Okay, so now we'll go on to question 4. Now, question 4 starts to get a little bit harder. So I'm going to go back to the 5-step method now. Okay, I'm going to explain this in a little bit more detail. Oh, someone's in here. Okay. I mean, question 4. So I'm going to now, okay. So I'm going to like expand the 5-step method again. Like question 4. Okay. Question 4 asks a question that seems simple. I mean, it is simple to express, but it's a lot harder to solve than question 3. Question 4 asks, at the equilibrium position, what is the instantaneous speed? Right? Like that's the question for this question. So so I so what I noticed right away, what I noticed right away is now it's not asking, well, it's asking for instantaneous speed, v. That might make me think of my old equations from physics 203. I might think things like, oh, I can relate speed to acceleration, right? Like I could do something like v equals at plus v naught, or v squared minus v naught squared equals 2ax, or something. Like I might, and I might be thinking about F net equals ma. In other words, I might continue to think about accelerations and forces just like I was in the last 3 questions. But I realize that first of all, um, I realize what I just said above in question 3. I realize, wait a second, the acceleration is not constant from one place to the next. The force is not, because the force is not constant from one place to the next. So all of my constant acceleration equations from physics 203, the kind of things that I was just using in the last 2 questions, they don't apply anymore. I have to think of this in a different way. I have to think of a different general definition or principle to solve this kind of problem. Sorry, hold on. Which happened to pen? Sorry. 1 second. Okay. When force varies as a function of position, like dot, dot, dot. So I'm about to give a GDP here. I'm starting it in English. I'm going to write a principle down in English, and then I'm going to like write it mathematically, but step 3s can be in English. When force varies as a function of position, when the force is changing from place to place, or put another way, when all the forces doing work on a system are what we call conservative Okay, here's the English. Of course, I'm going to write this mathematically in a second. But what I'm saying in English is if you have a situation where the force acting on the system is changing from place to place, is varying as a function of position, when you have that situation, or put another way, put in more fancy terms that I will define and expand on in a few minutes, when all the forces doing work on a system are conservative forces, then we say that the system conserves, like maintains the same value, holds constant, conserves total mechanical energy from place to place. Like the total mechanical energy over here will be the same value as the total mechanical energy over there. As long as the force doing work is a conservative force, then all the energy at any one given place will be the same as all the energy at another given place. Now, that's a mouthful. That's English. I still have to explain that further in a few minutes, but that is the concept that we're dealing with here. And let me also say, we're dealing with this concept now, like why I even am thinking to bring up this concept of work, or why I'm starting to introduce work and energy, is precisely because forces and accelerations will no longer help us. Once we realize the force is changing from place to place, we have to use a way of thinking in physics that tells us how to get information from place to place. That way of thinking is called work and energy. In fact, work is force applied from place to place. Okay, so this is the concept that we're now using. This is why we're now using it. What does it look like mathematically? What I'm saying here is this. Well, okay. It's getting a little sloppy, but the equation that I'm going for here that we're going to start like solving mathematically is 1f mv squared plus 1f kx squared over here at one spot equals 1f kx 1f mv squared plus 1f kx squared over here at the other spot. Like that's the equation I'm going for. That's what I'm going to solve in a minute. I'm just trying to explain it a little bit first in English. Now here's what's your job? The first, and this is true in homeworks and in exams in general, the first time you're going to introduce a concept in a document, you want to kind of over explain it, just like I'm doing now. If it's the first time the concept's coming up in the document, go a little extra mile to make sure that the concept is coming from somewhere and makes sense, that it's just not coming out of left field, right? That's what I'm doing here. I'm going to in other words, do I expect you to do something like this in your homework for this? Yeah, something like this. Doesn't have to be my exact words, doesn't have to be this detailed. But when in doubt, if you're about to introduce a new equation, a little bit of English is very helpful, right? And then once you explain the background of the equation or like why it's coming up, then you don't have to do that again every single in the rest of the document. Just like I won't. Okay, you get my point, I think. Um, so what I'm going to do here, I'm going to keep going, just like you would in your homework. Like I'm going to go to step 4 and start plugging in numbers and get an answer and all that so that we can move forward. But I'm going to warn you too that after we're at a certain point in this homework, I am going to back up as the teacher. As the teacher, I'm going to back up and really explain to you what I mean by these words, like work and conservative and all of that. And I'm going to really explain to you where this potential energy thing came from and all that. So, so bear with me. Like I first just want to get these answers here so that you know if you're doing the homework right or not. Okay. Or I'm sort of, okay. But then I am going to back up and unpack this for the sake of the class. And I'm going to unpack it in a way that you don't have to write all of that in your homework. I hope that's clear. But I first, just so that we're on the same page, I'm first going to get like answers and stuff. So this was all step 3, right? The key step 3, really, the GDP is 1F mv squared plus 1F kx squared over here equals 1F mv squared plus 1F kx squared over there. And again, if you don't exactly know where that came from, I'm going to explain it more, like by the end of today or by next time. I promise. But if you sort of know where it came from, then I'm going to use it right now. So here we go. So now I'm on step 4. Okay. I just made one slight modification. Oh, yes, absolutely. Direct chat person whose laptop is dying. I mean, whose iPad is dying. Yes, you can rejoin. I'll let you back in. Yes, if that's, or did you already leave? Yeah, I'll totally let you back. Yes. Um, okay. But thank you for asking. Okay.
Professor, why did you write it x equals to 0? Isn't it k?
Isn't it K? Okay, wait. That's a very good question. That's totally what I'm about to explain. It's a very good question. But I don't know what you mean by isn't it K though? Wait, isn't it K? Well,
K, like the k of the spring.
yeah, but what it is K. Wait, isn't it K? Well, okay, I'll tell you why. Okay, tell me if this makes sense to you. This is what I'm saying to everybody. Okay, from here on in. So I'm about to use energy conservation and work. Uh, you may know about work, and all of you might know something about work and energy. But if you're like me at all, you might know how to do it, but you might never know like when am I supposed to do work or energy? How am I supposed to know when suddenly to introduce energy when I was doing forces and accelerations in the last problem? And this sounds like I'm not answering Lear's question. I promise this is about to be an answer to Lear's question. What I want to tell everybody as a problem-solving technique is whenever you have a situation that you know the speed over here and you want to know the speed over there, like whenever you have a speed to spot correspondence, that is a big signal that we should use energy conservation. Because, and again, I haven't answered Lear's question yet. I'm about to, but I want everybody to know, like, in terms of when energy conservation applies and how it applies, energy conservation is all about when forces change from spot to spot. I mean, like place to place. And energy conservation is occurs. I mean, energy is conserved from place to place, as opposed to like momentum conservation. Momentum is the same value from one time to another. Like that's a whole different thing. But energy, we think about when we're comparing one place to another. So now to Lear's question. So I'm saying the total amount of energy, all of the kinetic plus all of the potential at any one spot must be equal to the total amount of energy at any other spot. So that's in general true. That's GDP step 3. So what spots do I look at? Which 2 spots? Well, my answer is I compare a spot where I know the speed to a spot where I'm solving for the speed. It's always a spot that you know, a place, a position that you know, compared to a place that you're solving for. So to answer Lear's question, what I'm saying here is, at x equals 0, x equals 0 is the place that I'm solving for. It's asking me, sorry, I don't know how that got erased. It's asking me, what is the speed? What is, sorry. It's asking me, what is, it's asking me, what is the speed at the equilibrium position at x equals 0? Like it's asking me for this at that position. So what I'm going to say is, I don't know offhand, but I know the speed. I know the speed at x equals x naught. Like I know the speed is in fact 0. It was given to me at the beginning of the problem. So I think this answers Lear's question. So I'm saying I'm going to pick 2 spots and believe that the total amount of energy, all the kinetic plus all the potential, must be equal at those 2 spots. One of the spots is where I have the information, and the other one is where I'm solving for the information. And where I'm solving for is x equals 0. So I'm not sure. Does that answer your question, Lear?
I think so.
You think so?
I
Okay.
think so.
Okay. That's fair. All right.
Okay,
Well,
thank you.
no problem. All right, let it sink. But in 5 minutes, if it's still not, well, yeah, let it sink in or see what I do, and then feel free to ask again. Okay. All right. So okay. So this is what I have. So now what I'm going to do, I'm going to try to solve for this, right? I'm going to try to get the answer for V at x equals 0. But to everybody to note, because I think this question is like a little harder than the last one, what I'm still in step 4 now. I'm going to do the work. I'm going to do the algebra or the calculus or the trigonometry. I'm going to do the algebra. But notice that while I'm doing it, I am going to leave actual numbers for the last possible moment. I think that's the correct habit to get into in physics, especially because you're going to see in this physics class, like we have more and more problems that are more and more abstract and don't even have numbers in them. So it's a really good habit to just work on the physics as long as you can, and then put in the numbers at the last possible minute. Also, then just in case you make a calculator error or something like that, it won't bleed through like all of your work. You could just you see what I'm saying? So what am I going to do? I look at this and I say, I try to simplify it as much as I can before plugging in actual values. So at x equals 0, where I'm solving for V, at x equals 0, this might be Lear's point. I'm not sure. At x equals 0, if I plug in my mind 0 for x, then that entire second term goes away. Like if x equals 0, then this entire term goes away to 0, right? And which is going to make my life a lot easier. Similarly, on the right-hand side, when x equals x naught, excuse me, when x equals x naught, the initial position, there is no velocity yet. Like that's where it was held at rest at first. So at the beginning, v equals 0. This entire term goes away, right? So I'm going to cross them out. So now my algebra is about to get a lot easier. I want you to note, though, like part of the reason I'm doing the step method, you're going to see when I go to question 5, like the principle here, the law, the equation is all of these 2 terms must equal over here, these 2 terms over there. That's the law. Then in this particular situation, step 4, I'm seeing, oh, when I apply this law to this situation, oh, I get a 0 over here. So that term goes away. Oh, I get a 0 over there. That term goes away. So it gets simplified for this situation. But this is like a spoiler alert or pro tip. Like when we get to question 5, you'll see it's the exact same question. We're going to set it up the exact same way. But then not as many terms are going to cancel out. So we're going to get a very different kind of answer. This is where it's very important to see the difference between step 3 and step 4. If you skip straight to step 4, well, you'll see. I don't want to. You could very easily get the correct answer for question 4 and then the wrong answer for question 5. If you do the steps properly, you'll get the correct answer for both. You'll see what I mean. So I'll keep going. So I have now 1/2 mv squared over here at x equals 0 must equal 1/2 kx squared over here at x equals x naught, right? That's what I have so far, that right? Now I could divide both sides by 1/2. I mean, I could have done this part before, but I didn't. I divide both, I factor out a 1/2, multiply both sides by 2, however you want to say it. And now what am I solving for? I'm solving for V, right? So I'll rearrange in terms of V. I'm postponing the numbers as long as I can. I'm just doing the physics now. So I go like, okay, V squared equals KX squared over M, right? So V equals the square root of KX squared over M, yes. So this is all still step 4. I'm just recopying. Right? Now I can plug in the numbers. Well, and it's a good, well, sometimes it gets complicated, but actually I'm going to leave. It's a good habit here when you're to think about the units and scientific notation and all this kind of thing. Right. And now now I'll put the numbers in the calculator. And if you really think this through, I'm kind of skipping steps right here because I want to make a point, because I'm watching the clock. I want to make a point. If you if you really track your units. Okay, this is like a sidebar, but notice the units really do work. Like paying attention to units is a check on whether your logic is correct, even before or once you put the numbers in, you can see if you're doing something at least not wrong by looking at the units, because a Newton is a kilogram times a meter per second squared, right? Like a Newton is a unit of force. Force equals mass times acceleration, right? So a Newton is a unit of mass times a unit of acceleration. It's a kilogram times a meter per second squared. So a Newton times a meter is a kilogram meter per second squared times meter. It's a kilogram times meter squared per second squared, all over kilograms. So at the end of the day, what we're going to get in this square root is meter squared per second squared. When you square root that, you get the units of speed. That does not prove that I'm getting the right answer, but it's definitely a strong indication that I'm on the right track, right? Like I'm doing something. I mean, if the units didn't work, I'm definitely wrong. If the units work, it's a strong suggestion that I'm doing something right. anyway, that all goes into step 4 is checking the units. So now we're
Professor,
almost there. Oh, sorry. Yeah. I'm sorry.
I have a question.
Yeah.
With regards to the equations, right? And the formulas, are we supposed to memorize all of them?
That's a really good question. So the simple answer is no. I mean, the short answer is no. You do not have to actively memorize anything for a couple of reasons. Number one, like you get equation sheets during the exam. So you don't have to actively memorize anything. Fair question. But the one like twist to that is I do want you to know the difference between a known given step 3 GDP versus something that you derive. Like you don't have to memorize anything. Although I do think if you do enough work and you do these things enough, you're just going to accidentally, you're going to remember things just because they make sense and they will, but you don't have to actively memorize anything. But you'll see, it's a very good question. You will see when I get to question 5. Like what I want you to know is this thing right here that we started with, this thing at the bottom of the page, like you don't have to memorize that, but if you ever were to try to memorize anything, or if you were ever to look on a list of things, that would be on the list. That is a law for certain situations, right? That is a step 3 GDP. When you get to this point right here, it says 1f mv squared equals 1f kx squared. That I actively want you to not memorize. Like, I'm going to make a bigger point about this in question 5, but that thing right there in the middle of the page is something that people accidentally do memorize and they think it's some kind of a law or some kind of formula or something, and they use it a lot, and it's not. I'm not saying it's wrong. Like, it's clearly correct here because it got derived here because we crossed out certain terms. So it applied here, but it's not a general law or something like that. Like if you write it down to solve question 5, you get the wrong answer for question 5. Like I'm going to show you that in a minute. So my long answer to Mohammed, it's a very good question. My short answer to Mohammed is you don't have to memorize any equations in this class. You do not have to. But my slightly longer answer to Mohammed is what you do need to know is the difference between a real equation and a derived equation. That's partly where step 3 comes into play, like knowing what is actually a given, such as that, versus what you're just deriving along the way, such as that. So that's a long answer. I hope that's clear, but you
Yeah.
don't have to actively memorize anything. No.
Okay. All right,
Okay.
thank you.
Thank you. Okay. Okay, so here we are. We're almost done with this. So now we're going to put in the numbers. All right, we already dealt with the units, so now I'm just trying to get the computation, so I'm not worrying about the units anymore. Right. But now, one thing, before I punch this into I think that's it, right? Yeah, before I punch this into the calculator, also, we should be very careful about one. I mean, this is like a technical point, but the question said, oh, wait. Oh, yeah. Oh, wait, actually, no, you tell me. Does the question ask for speed or velocity? This is a good way to see if anybody's paying attention.
Velocity.
Is that what it says? Is it?
Yeah. Wait, is it?
Wait, I think it actually said. And by the way, well, hold on. You get points for participation no matter what. So thank you. And you used your voice, so you get points for that. Actually, it said, okay, I'm looking at the sheet right now. So it actually says in meters per second, at what instantaneous speed does the mass? Okay, no, so wait, couple quick things. So, but thank you for answering anyway. I want to say something about that. But so to everybody, first of all, the reason I'm asking this, I'm not trying to trick you, but since this question number 4, it's a little bit different from question 5. Question 4 says, what's the instantaneous speed? So that means I'm literally only going to take the positive value of this square root, right? Does everybody see? Like, if it had asked velocity, like technically, like this thing I hope everybody realizes by the time this mass gets to the equilibrium position, like it's been released from over here on the right, it's now moving to the left. It gets to the equilibrium position, it's moving to the left. So its velocity is negative, right? If the question asks for velocity, then I would be looking for the negative root of this. I hope that's clear to me, but it didn't. It asked for speed, so I'm just going to get the positive root in a moment. Well, I'll write it right now, right? It's this. I think I even said this. I'm not sure if I wrote it. Like, I think this is the answer, right? And I just changed my equal sign to a squiggly equal sign, not because I'm guessing or like I'm not like just suddenly giving up and making a random answer, but I'm saying when you do the square root, on your calculator, you get a whole bunch of digits, and we have to chop off the digits somewhere, so it's now an approximate answer, right? Okay, 3.87. But I also want to quickly make clear about the class. Oh, speed. Oh, thank you, Caitlin. All right. So, for example, and I'm serious about, I know this is weird, but I just want you to know I will not keep talking about this every day until we all get used to it. But, like, for example, Caitlin wrote in the chat, like, the answer to my question. She wrote speed. Now, and she's not the only one. Like, and I heard I mean, I know I don't even remember who it was. I wasn't looking, but maybe it was Antonio, I think. I mean, Anthony, not Antonio. Like Anthony, I think, like used his voice, right? Now, we already established he can submit to the portal that says speak now, because he used his voice and he can get points for that. But also he can double dip into the same portal that Caitlin can because they both just took a risk. They both just gave an answer to a question where their answer might have been right or it might have been wrong. That is a risk that I want to incentivize. So they both can go into the portal that says for right or for wrong, meaning they gave an answer that is like potentially right or wrong. And like Caitlin could screenshot what you just put in the chat, or Anthony could just like remind me, whatever. Who I think it was Anthony. And they can go into the portal that says for right or for wrong, which basically means taking a risk, as opposed to just like giving your feeling like my favorite color is blue. Like that can't be right or wrong. That whatever, you get my point. So they go in and they get the points. Now, let me say something extra that's a little bit surprising and weird, and I'm very proud of. And I don't mean to single anybody out, but the fact is, not only can they do that, or Anthony can do that, but then there's this other portal right underneath it you see in Google Classroom that says be wrong, be really, really wrong. Now, not only did it, and I say this with complete respect, really, but like Anthony, like, and stop me if I'm wrong. If it was, I think it was Anthony. It wasn't Anthony that like just had a conversation.
Yeah, it was me. I
Okay.
was.
Okay. So I'm not trying to single you out. This is about to be a compliment. Okay. I promise this is not to embarrass.
It's all good. Yeah,
Okay.
sure.
All right. Okay. So here's the fact. He said velocity, right? And it turned out, I mean, of course he was in good faith and it was like totally helpful, but it turned out that was like wrong. It actually was speed. So he can additionally go into the portal that says be wrong, be really, really wrong. And he can do the same thing, same conversation, same moment. He can remind me there. He's like, I said velocity, but actually you said it was wrong. It was speed. And he can get points for being wrong. Can I say that again, please? Honestly, this is of all the things I ever do as a teacher in the last 30 years, I think this is the thing I'm the proudest of, really. And I'm not kidding. You can submit for extra points any or all times that you actually like are wrong in the class discussion. Okay? For real. Because that is how important I think it is for people to take risks and experiment intellectually, not just in the lab, but in a group discussion. Physics and science is about experimentation and taking risks. And we all know that in the lab, but we all forget that, or it's like harder to do in a weird way in group discussions, like especially on Zoom or this and that. We are here to take risks and be willing to be wrong and to find out that it is not a crisis, that it's not the crisis, and that even if I'm talking about this for way too long and it might be a little bit embarrassing, like people should not be ashamed of being wrong here, including me. Okay. So anytime you actually take enough of a risk that it turned out that you were actually like wrong. And that could even be in direct chat. I'm not saying you have to be public about it, but if I ever say someone is wrong, hopefully I'll say it very politely, but they should submit for extra points for that. I'm dead serious also, and I'll be done in a second, but I mean, I really think it improves all of us if we're willing to be wrong and find out that it's okay, especially in science, where we've kind of been tortured for years into being afraid to be wrong, or certainly I was. I'm not talking about your professors. Um, so I mean it so deeply that also, there's like a portal where if you correct me, then you get points. If I'm wrong, right? I think it's called respectfully corrected. Like, yes, I want you to correct me with respect. Like, don't shame me. Just like, hopefully you'll find that I don't shame you, right? But if I'm wrong and you point it out politely, you go to the portal that says respectfully corrected. If you're wrong and I point out politely, you go to be really, really wrong. And it's automatically a double dip. Because if you're wrong, that means you also took a risk of either being right or wrong. So you can always put it in both the portals. Last thing, what is to stop you from every single day just like making up something and being wrong in front of everybody to get the point? Nothing is to stop you. Like challenge accepted. Like, go for it. I'd love to see it happen. The reason I can do this crazy system and literally give you points for being wrong is that to this day, no one's ever abused it yet, because we all have way too much pride and way too much fear of being that wrong that frequently in public. Like, I mean, I encourage you to try. I encourage you to try to cheat the system and be wrong every single day and get a bajillion points. Like, really, I hope you understand what I'm saying. So, okay. So velocity is not a vector. Okay. Velocity is not a vector. Oh. I just got it. But Latchman just got points. I'm serious. Like, and that's funny. I should really open a portal too for like comedy, like, because it's helping us all. But no, I like, just so you see. Yes, I see what Latchman just did. He can screenshot that and he can submit it for points for being wrong, and he will get the points for being wrong. And if somehow he does that every single day, then Quark bless Latchman and Quark bless America. Because first of all, it'll entertain us all. We'll all pay that much more attention to class. Like, really. Like, I challenge any of you to try to be wrong every single day. It won't break the system. It will just improve you as a scientist. I'm really serious. If I had gotten over my fear of being wrong decades before, I would be a much better scientist than I am now. Like, really. But okay, isn't velocity? Yeah, he's kidding. I mean, I believe, like, velocity is okay. Now I guess this is the risk. Okay, we don't want to confuse people. Velocity is a vector. Latchman is joking, I believe. Latchman is on purpose being wrong to test my system so that he can get points. I believe. Tell me from. So he's not trying to confuse you, Mohammed. I mean, like, wait. Yes, I am. Okay. So I better move on now before I create total chaos. But I am serious. I mean, it's 1:13. Yeah, I'm going to move on, but I hope you get my point. I hope you get my point. Okay, so that's the answer to that one. Sure. Okay. And those of you who just did that, like Latchman and Mohammed, when you wrote sure, that is called closing a conversational loop. You can submit that for those points. Really. Okay. Now, because I'm going to go to question 5 now. I'm going to do a little bit faster this time. Question 5. Well, yeah, okay, I'll do it a little bit faster. So step 1. So for diagrams, see above, you don't have to do that every time, right? But then step 2, what is the question? Well, question 5, the question is when V equals 3 meters per second, what is X, right? That is the question for question 5. Yes. So notice, this is, and I think most of you did notice this is really the same question as question 4, but in reverse, right? This is again a speed spot correspondence. Question 4 asks, at this spot, what is the speed? and it assumed you knew the speed at some other spot. So it was really asking you to say, if you know the speed at one spot, what's the speed at the other spot? Now we're doing that in reverse. We're saying, if you know the speed at the spot over here, or if you know the spot at which there is a certain speed, what's the spot where speed of 3 occurs? It's just the same question, but in reverse, right? So I'm totally am going to use the same step 3, the same GDP, and I don't have to re-explain the whole thing again. So step 3, GDP, I'm just going to say, this is once again a speed to spot correspondence. That is not a technical physics term, by the way. When I say speed to spot correspondence, I mean like speed to position, right? I'm just saying it that way because it's easier to remember, but I hope you know what I mean. Speed to spot correspondence. So the GDP again is okay. So I'm doing the exact same GDP as before. Now watch. Okay, we have 14 minutes. Same principle as before. The total energy, the potential plus the kinetic over somewhere must equal the total kinetic plus potential somewhere else. And just like before, the somewhere that I'm looking at is the somewhere that I'm solving for, where I don't know something. And the other spot that I'm comparing it to is where I do know something. What do I mean by knowing something? Well, just like before, I'm going to compare to x equals 0. I'm sorry. Oh, I could do that. Actually, I could, but I didn't mean to say that. I mean to say x equals x naught, just like before. Now, either the truth is, like, because at x equals x naught, I know the speed is 0. So I'm just going to use that again, just like I did before. Now, the truth is, just before I found out the speed at x equals 0. So I could now use that as my known spot. Either way, it'll be fine as my known spot. But what's my unknown spot? What's the spot I'm solving for? Well, the spot I'm solving for now is literally the spot called x, the position called x. Like that, it's x equals x. I don't know what the x is. That's what I'm solving for. I know that it is the x for which v is going to equal 3, right? Okay, so my first point is back to like memorizing equations or whatever. I'm not saying you have to like literally memorize this, but what you have to notice is because this question is the same as the other question, the same format as the other question, I'm using the same principle to solve it. And the principle is total energy over here must equal total energy over there. Now I go to right, like what I did not write down is this thing in the middle of the page. I did not write 1/2 mv squared equals 1/2 kx squared. That is not a principle. That is not an assumption that we can make. It turned out to be true for question 4, but question 5, it won't be true, and you'll see why. Because now if I go through slowly, so step 4. If I go piece by piece, okay, at the spot X, where I'm going from left to right here, at the spot X where I'm solving for, I ask myself, is V 0? No, it's not. It's not 0. It's 3. Like the spot that I'm solving for but according to the given of this problem, I'm solving for the spot where the instantaneous speed is 3. So I can't cross out that first term. Is x equal to 0 at the spot I'm solving for? No, it's not. It's some x that's unknown. I know it's not 0 because when x is 0, the speed is a lot higher. It's 3.87. I just figured that out in the last question. So no terms on the left side get crossed out. That's my big point. On the right side, do any terms get crossed out? Yes. Kinetic energy, V at x equals x naught. Yes, that still equals 0, just like it did before. What about x? Well, x is 0.15 and x naught, so that doesn't get crossed out. In other words, I know I'm dragging this out again, but what I'm really trying to say is that I only cross out one term this time, not two. So I cannot say that 1/2 mv squared equals 1/2 kx squared this time. That's why that is not a memorizer, so to speak. That is not a step 3. So I'm going to do out the math, just in case I run out of time. I'm going to do out the math right now. I'm going to get the answer 0.095. That will be the answer. If you get the answer x equals 0.095, you're good. I mean, just hang with me for a couple more minutes anyway, but that means you are understanding something. If you got the answer 0.116, I'm not shaming you. I'm not then you're not alone. Many people for this question, for question 5, get the answer 0.116 or something like that, or 0.113 maybe, something like that. If you got that, you're not crazy, you're not irresponsible, you're not a criminal, but you are wrong. If you got 1.116, or I think it is, that's a very common wrong answer. That's the answer you get if you just said 1/2 mv squared equals 1/2 kx squared. So I'm just trying to alert you that there is something to be paying attention to here and to think about at home or correct. The lesson here is the step method, steps 1, 2, 3, 4, 5, really help, and particularly help those of you who might have thought the answer is 0.116 in this case. But all right, but it isn't. So what do I do? So I'm solving. So what do? I'm solving for x, right? So I'm going to get it by itself. Whoops, sorry. I'm going to say 1/2 kx squared, getting it by itself, equals 1/2 kx squared minus, in other words, I subtract 1/2 mv squared from both sides, but the kx's are different. Like this is the x that I'm solving for, and the other x is x naught. They're not the same x's, right? Now I can factor out a 1/2 from each side and divide both sides by 2, so the 1/2s can all go away. And then I can say x squared equals x. If I can do this, and again, to some of you, it might be easier to picture this with plugging in the numbers first. I understand that, but I really want to challenge you or encourage you to try to get used to not plugging in numbers yet. It will be a good habit for the rest of this class to postpone the numbers as long as possible, right? So I get hey, oh, the board just froze. Okay. Right. Now on this one, I think the units are going to get a little cumbersome. I'm going to skip the units for right now, also watching the clock. So I do something like this. Right. And now we're almost there, right? But now I look at the question. This is where the question said at what, well, the literal words of the question were, in meters, at what position does the mass achieve an instantaneous speed of 3 meters per second? Right? That's what the question. So now, it said speed again, not velocity. It's asking at what position does the mass have a speed of 3? So if you back up and think about that if the speed is 3, that could mean that the velocity is 3 or the velocity is -3, right? Stop me if that doesn't make sense. But if the magnitude of the velocity vector is 3, that means the velocity vector could be 3 or -3. And physically, what I'm saying is we're looking for a spot where the thing is going a certain amount of speed. It might be when the thing is going, it might be the spot that it passed. Excuse me, three, the number three is bigger than zero, but it's smaller than 3.87. So the first thing that comes to my mind is we're looking for some spot on the way from the initial position to the equilibrium position, right? Somewhere in between 0.15 and zero, right? When it hits somewhere in between there, it's going to hit a speed of 3, but technically a velocity of -3 because it's like going that way. But then it's going to pass through the equilibrium going really fast, going 3.87, and start to slow down and start heading to the other side. Well, it's going to slow down to 3 again, going that way. So and actually, now that I think about it, technically it's still going to be going negatively with a velocity of 3. So there's going to be another spot on the other side where it achieves this same speed again. And then it's presumably going to keep doing it back and forth, back and forth. So, long way of saying, I think now, really, if we're really being careful and reading the question carefully, I think we're looking for 2 routes now. I think there's 2 spots, the positive route and the negative route, where this thing could achieve a speed of 3. I hope you agree, or I think you agree. So I think once you do the numbers on your calculator, you get approximately. So when v equals 3 meters per second, x equals. So that's the final, plus or minus 0.095 meters. That's the final answer to that. There's more. Okay, I'm going to pause on that. We have like 4 minutes. I'm going to pause on that. Like I said, we still have more to do. I still have to get to questions 8, 6, 7, 8, and 9 on the sheet. There's a lot to be said about question 9. So there's still time for us all to be working on this homework. And even honestly, even what I just did, even all this 1/2 kx squared plus 1/2 mv squared, if you're sort of following the computations, but you're still a little foggy where I got 1/2 kx squared plus 1/2 mv squared, that's fine. I understand. Next week, I am going to back up and kind of unpack the math behind that because we need it for later in the course. In other words, on Monday, I'm going to expand more on the integral that we use to calculate work and energy, and I'm going to expand on the dot product that we use to get work. So that's what those equations were right at the beginning of the board today. Like I didn't get to them today, it's fine. Like I'll get to them on Monday. So bear with me. Again, there, as I mentioned, there's like a lot to go over in sheet 1, in homework sheet 1. For some of you, it's review. For some of you, it'll be very freshly clarifying. But I just want us all to be on the same page before we move on in the course. So that's the answer to that one. We have 3 minutes, but I will just tell you so that you have perspective for the answers for the next couple of questions, just so that you know. I think for question 6, the answer is negative 0.15 meters. This is just so that you can know like whether you're doing things correctly or not. You still have to show work and all that, but I think that's the answer for question 2. For question 7, I think the answer is infinity. Like it'll make an infinite number of trips back and forth. Okay. And for question 8, I'll just tell you, now I'm going to have to talk about this. Of course, I'm going to explain this, but just so you know the answers. I think for question 8, velocity, like the magnitude of velocity is going up. The acceleration is going down. And I believe that the jerk is going up. A lot of you say it's constant. I understand that, but I don't think that's right. So I would encourage you, especially for question 8, even though it looks like English, it doesn't look like problem solving, still explain your reasoning, do the steps, like do the steps. Even for question 8, because if you really think through question 8 in a careful way, that will help launch you into question 9. And again, let me say with question 9, even though it's super hard, and all of us probably at some point need help with question 9, which I will give, you could still start question 9. You can do steps 1, 2, and 3 for sure, especially if you think hard about question 8 before you do question 9. But okay, it's 129. Great. Oh, there's one more. Great questions in the chat. Amanita, Amanata. Sorry, Amanata. Okay, so I'm kind of loose about it. It's not like chemistry. I'm not like super rigorous about significant digits. When in doubt, you don't want to give more significant digits really than the problem originally gave you, than the question gave you. Generally, my rule of thumb is 3. I generally try to go to 3. I try to phrase it with 3 in the question and keep my answers to 3. So that's my rule of thumb, but you don't have to go crazy about it. And then I think great question in the direct chat. I'll just say really quickly, you can all go. Wait, goodbye. Thank you. Have a great, but I'm here to answer a couple quick questions, but have a great weekend. I'll turn off the recording also, but there's